Alright, in this problem we have this 40-pound wheel which is attached to a spring, and we apply a 15 foot-pound moment to it, and it makes our wheel rotate and move towards the right. We want to figure out what its angular velocity is after its center of mass g has moved 0.5 feet to the right. So after g has gone sort of to this position, and this is our new g. And I want to do this by using the principle of work and energy. And that says that our initial kinetic energy plus the sum of forces that do work on our system is equal to our final kinetic energy. And since we're rolling and we're translating, this is undergoing general planar motion, and it's a rigid body. It has some dimensions, it has some moment of inertia. So our kinetic energy, T, is going to be equal to 1/2 times the mass times its velocity of its center of mass squared, plus 1/2 times its moment of inertia about its center of mass times its angular velocity squared. And this right here is the translational part of its moment of inertia, of its kinetic energy, and this right here is the rotational part of its kinetic energy. And because at the beginning it's at rest, it has no velocity, its initial kinetic energy is going to be equal to 0. We just need to figure out what forces do work on the system. Now, if we draw a free body diagram, we're going to be able to figure that out. We're going to have a normal force that acts back up. We're going to have a weight force that acts through our center of mass. We're going to have a frictional force that, because it's rotating this way, it's going to go against that rotation, so it's going to point towards the right. We're going to have a spring force that's going to point towards the left. This spring force points towards the left because as we move and stretch this spring out, it's going to want to come back to its unstretched position, which it is right now. And finally, we have this moment right here, which is it's 15 foot-pounds. Okay, so which forces do work? Well, we know our normal force doesn't do work. It's always perpendicular to our direction of motion. So our normal force never does work. Because the problem says we roll from rest without slipping. Without slipping means our frictional force is going to do no work, since our wheel does not slip. And finally, our weight does no work because we're not changing height. Everything is on the same plane. It's only in the x direction. It's not changing any height in the y direction. So our weight does not do any work. So the only two forces that do work is this moment right here and our force of our spring. So let's look at the moment. The work done by a moment, since it's constant, is going to be equal to the magnitude of the moment times the sort of change in angle that it rotates through. So it's final angle minus the initial angle it's at. And what we're going to do, we're going to say it starts at a initial angle of 0, so it's just going to be equal to m times its theta 2. And it's important to note that these angles are in radians. So this is equal to 15 theta 2. Now, what's our force of the work done by our spring? Well, the work done by our spring is going to be equal to minus 1/2 times our spring constant, which is 10, times s, the amount that our spring is compressed or stretched past its unstretched position. And this is going to be subtracted from 1/2 times the spring constant times if the spring is stretched or compressed in its initial position. Now, we're told the spring is initially unstretched, so that means this right here is going to be a 0, which means this part of the equation goes away, and this right here becomes the work done by our spring. So if we put these two work in for this part of the equation, and we put this kinetic energy in for our final kinetic energy, we'll see where that gets us. So let's do 15 theta 2 minus 1/2 times 10 times the position my spring is stretched squared is equal to 1/2. I'm going to start putting in all my knowns, times 40 over 32.2 times the velocity of my center of mass squared plus 1/2 times my moment of inertia about my center of mass. And we're given a radius of gyration, so this right here is going to be my mass, which is 40 over 32.2, and I'm dividing it by 32.2 because I was given a weight and I have to take out gravity, times my what did I say? My radius of gyration squared, so 0.6 squared, times my angular velocity squared. So I have just a little bit of a problem right here. I have this term, this term, this term, and this term, but only one equation. So I'm either going to have to find a numerical value for some of this, or I'm going to have to relate them to find an expression that relates them to my angular velocity, because that's what I'm actually looking for. And we can do that. It's not really that big of a problem. If we take a look at this wheel, we'll notice that at this point right here, let's call this point B. At this point right here, my velocity of B is equal to 0, because a wheel that's rotating on the ground at that instant has a 0 velocity at the point of contact. So this is my instantaneous center of 0 velocity. And we know my center of mass is right here. And we can relate the velocity of my center of mass to my angular velocity using methods of instantaneous centers. So we know the velocity of my center of mass is going to be equal to my angular velocity times the distance of my center of mass with respect to my instantaneous center. Now, that distance is going to be this length right here, r of g with respect to IC, and we know that's going to be equal to 0.8 feet because that's just the radius of my disk. So this is going to be equal to 0.8 omega. Okay, that's good. I can now substitute this into my equation right here, and I have a velocity of my center of mass in terms of my angular velocity. So that's good. Now onto these two parts of the equation. Well, what am I going to do? Well, again, I can use parts of this. I can say that the distance my center of mass travels is going to be equal to some distance some angle it rotates times the distance from the center of mass to my instantaneous center. So right here we're going to get, this is going to be 0.5 because it moves 0.5 feet. It's going to be equal to some theta, and this again is going to be equal to 0.8. So I know that the amount that I rotate, theta, is going to be equal to 0.5 over 8, or 0.625 radians. So right here, I now know how far I rotate. I know I rotate 0.625 radians. So I can plug that in for theta 2. That's a numerical value. That's good. I have one more variable that I don't know. I don't know what this S2 is. And my S2 is going to be how far my spring stretches past the unstretched position. And it's going to be at this point right here. And let's call this point A. So with this sort of same method I've been using, I can say the distance that A moves, this SA, SA is going to be S2. So I'll just call this S2. And this is my second point. So S2, the distance that I move, is going to be equal to theta, how far I rotate, times this R of, I guess I still call it A, of A with respect to the instantaneous center. And this is going to be 1.6 because this right here is 0.8 feet, this right here is 0.8 feet, 0.8 plus 0.8 is 1.6. So the distance that this moves right here, that I stretch, is going to be equal to theta, I rotate 0.625 radians, times this 1.6 feet. And I get that this distance that A moves and my spring stretches is going to be equal to 1 foot. So now I can rewrite this equation right here, plugging in all the knowns that I just figured out. And I get 15 times this 0.625 minus 1/2 times 10 times 1 squared is equal to 1/2 times 40 over 32.2 times 0.8 omega squared plus 1/2 times 40 over 32.2 times 0.6 squared times omega squared. And look at that. Right here, when we square both these terms, we're going to get an omega squared. So we're going to have this entire equation in terms of omega. And we can solve for omega, which is our angular velocity. And we're going to get that omega is equal to 2.65 radians per second. And this is our answer.